In this video, we're going to look at three-dimensional geometry using the VSEPR model. VSEPR stands for Valence-Shell Electron-Pair Repulsion theory. It's just a model that we use to predict the geometry by counting the number of groups surrounding a central atom. We assume in this model that each atom will minimize the repulsion between these groups, or effectively that means they'll be spread out as far apart as possible. If you hear the term electron geometry, we're referring to the orientation of electron groups about a central atom, whereas the term molecular geometry indicates the orientation of atoms about a central atom. The key difference here is the electron groups versus the atoms. When we're talking about electron groups, we count a lone pair, a single bond, a double bond, and a triple bond as an electron group. For example, something that has a lone pair and 3 single bonds, that would count as 4 groups. A triple bond and a single bond would count as 2 groups. In electron geometry, you count the number of groups and then use this to predict the geometry. You will find that typically the molecular geometry and the electron geometry are the same. However, if one or more of the electron groups is a lone pair, then the molecular geometry and the electron geometry will be different. In these examples here, the electron geometry and the molecular geometry are the same. In this first example, we're looking at the geometry about the central carbon here. So effectively, we're looking at the carbon-carbon-nitrogen geometry. We have 2 electron groups attached to the carbon, a single bond and a triple bond, and neither of those are lone pairs, so both the electron geometry and the molecular geometry is considered to be linear. Linear geometry means that we have a 180-degree angle between those groups. In the second example here, we're looking at the geometry about this central carbon. So we're looking at the carbon-carbon-oxygen geometry, and this should be approximately the same as the carbon-carbon-carbon geometry. You can see that we have 3 groups, a double bond, a single bond, and a single bond about that central carbon atom. So both the electron geometry and the molecular geometry are the same because none of those groups are lone pairs, and we consider this to have trigonal planar geometry. And the angles here are approximately 120 degrees. In our last example here, we're looking at the hydrogen-carbon-carbon geometry, or looking about this carbon as a central atom. This should be the same geometry about the hydrogen-carbon-hydrogen bond. And if you're looking at this picture, the way it's drawn flat like this doesn't really indicate what's going on in the molecule, because the actual geometry is tetrahedral with a bond angle of 109.5. So we really need to use that dash wedge notation to explain what's going on. So the hydrogen here is sticking out, and this hydrogen back here is sticking back. So it's not 90 degrees like it looks like in that picture, but in fact about 109.5. And the angle is approximately the same over here between the hydrogen, carbon, and hydrogen. The electron geometry and the molecular geometry are the same, or tetrahedral. Here's an example where the electron geometry and the molecular geometry are different. The molecule shown here has a lone pair on the nitrogen. So here's that nitrogen shown in blue, and the angle that we're looking at is the hydrogen-nitrogen-carbon angle, or the lone pair nitrogen-carbon angle. In electron geometry, we count that lone pair, single bond, double bond, which gives us 3 groups or a trigonal planar geometry. However, if we're looking at the angle between the atoms, the hydrogen, nitrogen, and the carbon, the molecular geometry is in fact bent. So just keep in mind that when you're trying to visualize what's going on with the atoms, but if you're trying to figure out where the lone pair fits into all of this, then you would consider it to be trigonal planar. I usually prefer to think of the molecular geometry because I think that gives us a better picture of what's going on. Here's another example. In this case, we have a lone pair on a carbon. So you can imagine a hydrogen group sticking out and a hydrogen sticking back, and the lone pair is coming up in the plane of the screen. So if we consider the lone pair, we have 1, 2, 3, 4 groups, and we would have tetrahedral geometry. But if we don't count that lone pair and we look just at the atoms, we have trigonal pyramidal geometry. The angles that we talked about in the previous examples refer to the ideal bond angles. And these are the bond angles where molecules are more stable. If for some reason we have to deviate by that ideal bond angle and get smaller or get a lot bigger, then your molecule is going to be less stable and more reactive. Let's look at these examples here. So now we know that a carbon with 4 single bonds likes to have a tetrahedral shape. And in a tetrahedral shape, the ideal bond angle is 109.5. However, in cyclopropane, the molecule is forced into this 3-membered ring, and it deviates significantly from that ideal bond angle. In fact, the real bond angle is 60 degrees. So this makes cyclopropane highly reactive. You have the same problem in cyclobutadiene. The carbon here has 1, 2, 3 groups attached. So the geometry should be trigonal planar with an ideal bond angle of 120 degrees. But in cyclobutadiene, it's forced into this 4-membered ring with an actual bond angle of 90 degrees. Again, this is a highly strained ring system, and so this molecule is very reactive. That concludes 3-dimensional geometry for now.